Thank you all for coming. So I'm going to talk about some work which I've been doing for the last 1.5 or 2 years, and most of the work which I'm going to talk about is in the context of the Yahoo front page. And so before I begin, I would like to acknowledge. So first of all, this work would not be possible without the tight collaboration between Yahoo Labs, Yahoo Research, and several other folks in engineering, product. So I've not mentioned all of them here, but my chief collaborators in Yahoo Research are these three folks, so B. Chung, Pradeep, and Raghu Ramakrishnan. Okay, so let me begin with the motivating example. So some of the technology which I'm going to describe applies to many other applications which we are running at Yahoo, but let me begin with a motivating application which I'm going to use throughout the talk. Okay, so this is the Yahoo front page. I'm hoping most of you have visited it at least once in your life. So how many of you have not visited Yahoo front page? Just trying to gauge our market share. Okay, that's good. That's not bad. Okay, so this is the Yahoo front page, and if you go to the Yahoo front page, there are several content modules on the page. So there is one module which is called the Today module. This is a very important piece of module which is published on the Yahoo front page. So why do I say it's important? So first of all, the articles that get published on this module are generally links that take you to other parts of Yahoo. Like for instance, if there is a finance story here, it's typically going to take you to Yahoo Finance. If there is a sports story, it's going to typically take you to some page on Yahoo Sports. And if you go to Yahoo Finance, we have display advertising and other advertising. And so it's a big source of revenue for us. So this is an important model because it helps us route traffic to other parts of the network. So the module consists of 4 different slots, right? So I have labeled these slots as 1, 2, 3, 4. And the article that is displayed on slot 1 is the one that shows up over here by default. So this is a very important slot because whatever we show here is the one that appears on the page by default. So generally articles that are shown on this position have very high exposure compared to articles shown on the other 3 positions. If a user likes this article, they can click on this, and then this article is going to show up on this position. But this is the default, right? And it has maximum exposure to article. So this is really the motivating application. And so let me try to define what our problem is here. It's probably familiar to most of you here, but I'll just still go through it just to set up notations and the agenda for the next of the talk. So the goal here is to display the best articles on the Yahoo front page for every single user visit. So now the next question is, what is best, right? So how do you measure best? What is best? So best generally, abstractly, best is something which is going to maximize user satisfaction. Best is something that's going to maximize user engagement on the Yahoo front page and on the network. But generally these things are hard to measure instantaneously. If a user just comes in and he or she clicks on an article, it's very hard to know whether they were satisfied or not. Satisfaction is like a long-term measurement, which is not readily measured in the short term, right? So it is hard to optimize articles that we show to users based on such long-term measurements because they're very hard to measure. So what we do instead is we approximate this objective. We say, okay, well, our goal is really to maximize user satisfaction and engagement, but instead of measuring these quantities, which are hard to measure in real time, we are going to approximate and maximize some utility that is based on immediate feedback, which we can get. Right? So as soon as we show something to a user, can we measure something immediately? And something that is a proxy for this kind of long-term metric. And one thing that we could do is click rate, right? So if you show an article, if a user clicks, and so if there is a Michael Jackson story which is clicked a lot of times compared to some other real estate story, then probably users like it more. And that's a good proxy of what user satisfaction and engagement. Not a perfect proxy, but it's a good proxy, and it could be measured relatively easily. However, this is not the only objective which we maximize. Like if you start showing Britney Spears, for instance, it's going to click very well. That does not mean it's going to lead to an overall improvement on the recommendation on the Yahoo front page. So what we do is we impose some constraints, right? So we maximize click rate, but at the same time we make sure that our serving scheme has some constraints built into it. So one such constraint could be, okay, well, we want to make sure that our user is exposed to articles from different categories, right? So we don't want Yahoo to become a Hollywood gossip site, for instance, right? It's not always going to be Britney Spears because everybody clicks on Britney Spears. That's not what Yahoo is about. In the short term, we'll get a lot of clicks, but then the users are going to start leaving Yahoo because they're going to associate Yahoo with a Hollywood gossip site, and that's not what we want. So relevance is important, freshness is important. If there is a breaking news story, like if there is an earthquake somewhere in Somalia, sorry, there was no such earthquake, but if there is an earthquake, say in China, we want to show that story immediately on the Yahoo front page. We don't want to show it after a day because that's not a characteristic of a good portal. So it should be fresh and it should be diverse, right? So if a user comes, he should see stories both from politics, sports, entertainment, and right. So the next thing is what should our article inventory look like? That's an extremely important question when we are doing recommender system algorithm. What is your inventory from which you want to choose your articles, right? So in this case, since it is the Yahoo front page, we don't take any chances. We make sure that the articles which we choose from to show on that module are all curated by human editors. So we have very creative human editors who keep track of what's going on the web. So if there is a breaking news story about an earthquake, they are going to go to different news sources and assemble different snippets about that news article together into a very nice kind of story form and show you on the front page. Right? So that's how these articles are created. And so the number of articles from which we have to choose from at any given point of time is typically small. There are only 30 to 50 articles from which we choose from. However, the article pool refreshes periodically, right? So after an hour, if the editor feels that this story is stale and there is a new news story which should be put into the pool, they are going to replace the existing articles with some other articles that are more germane or more timely. This is how the article pool is decided. Okay. So before this research, the editors used to create articles, and they were the ones who decided which articles should be displayed when on the Yahoo front page. It was all done editorially. There was no machine learning or statistics or data mining at all. After this research, article placement is done through statistical and data mining models on the Yahoo front page or on the model which we just showed. So again, I get this question everywhere I give this talk. I get this question at the end of the talk. Are the methods you described in production? And which subset of the methods are in production? How successful it has been? So generally, it's a difficult question because it's not clear what you should reveal and what you should not reveal. So this time I made my life easier. I just got some quotes from our CEO, and I'm just putting it up here. So these hopefully are all vetted, and I don't have to be. I won't be in problems, I guess. So this is the quote which we had from last year, Q4. So again, the technology which I'm going to describe, that's called the content optimization technology with editorial expertise. And we have seen click rates more than double. And again, here she's talking about making additional improvements so that user experience is going to be more personally relevant. And this is what we have in Q1. So this thing was done, and now, so there are many other things here, but I'll particularly focus on this. So the result was 100% click-through rate increase over time. So in January, we introduced release 2 of the engine. So that is the personalized recommendation which is talked about over here, which included some of our behavioral targeting technology. So the behavioral targeting technology, what it is in Yahoo, we keep track of a browse signature for every user. The browse signature is reflective of what the user have been doing on Yahoo. Like if there is a user who visits the Yahoo Finance page a lot, then the browse signature is going to have a very high weight on finance for that particular user. If a user has been visiting sports a lot, there will be a very high weight on sports, for instance, right? So we're using these browse signatures to recommend articles to users who visit the front page, and the click rate improvement have been 160% over the pre-engine implementation. Just to give you an idea of what this, so this technology is live, it's working, and it's been reasonably successful, I would say. Okay, so the main, so this is what I'm going to do in the rest of the talk. I'm first going to describe to you methods which we use to select the most popular articles out of an content pool, right? So there is a content pool of like 30 to 40 articles at any given point of time. How do you select the best of the web? So this is the first problem which we attacked when we started this research, because that's exactly what the editors were doing, except that they were doing it in a very subjective way. There was no machine learning involved. So I'm going to talk about that. And again, this is a problem which comes up in many other places on the web, right? So there are many portals. If you go to portals, there will always be some section of the portal where you want to show the best of the web, right? So you can use the technology which I describe here to do that particular kind of recommendation. Then I'm going to talk about how to do personalized article selection, which this is something which is, in particular, I'm going to talk about how to personalize content based on user covariates. So covariates are, again, features which we construct for every single user. For instance, browse history is a feature which we construct for every single user. And then I'm going to talk about how we do personalized recommendation at the per user level. So the covariates are good, but there are many users in our system who are very heavy users, right? So there are front page users who visit the front page 3 times a day. Now for those users, so if you look at all users that are interested in finance, there is a huge variation in how they consume content. So there might be 2 different users, user A, user B, both of them are interested in finance, but if user A visits the Yahoo front page 10 times, his behavior may be very different from the other user, and we can actually learn about his behavior. We can distinguish or discriminate his behavior from the other Yahoo Finance user just because we have seen a lot of activity by that user on the Yahoo front page. So I'm going to talk about models that do per user recommendation, and this is again work that is based on extending matrix factorization methods that have been extremely successful in the case of Netflix. The only difference is we are going to use both the ratings as well as the metadata together to generalize the Netflix kind of methods. And finally, I would like to mention that although all these methods would be illustrated in the context of the Yahoo front page application I talked about, there are some other requirements when we actually built this method. One of the requirement was scalability, and the other requirement was the method should generalize to small traffic scenarios. So the front page portal which I showed you, that was the Yahoo US portal, where we have extremely high volumes of traffic. But we have similar modules running on other parts of the globe, like Yahoo France, Yahoo India, Yahoo Taiwan. So these portals run on many different websites at Yahoo, and for some of these countries, the traffic volume is relatively small compared to what we get on the US. So when we did develop this method, we had that goal in mind as well. And again, we have also been syndicating the Today module, which I talked about on Yahoo Mail. So for instance, if you sign into Yahoo Mail, immediately you see some module popping up, and that is actually exactly the Today module which we see on Yahoo front page. Similar things happen on Yahoo IM as well. If you sign into IM, there is a box, there is a window that pops up, and that also shows the same Yahoo front page Today module. So we have been syndicating this Today module in different parts of Yahoo. We are now trying to syndicate that to Yahoo Mobile, for instance, right? So it's important that it generalizes, right? So as I said, this is a generic methodology. So for instance, let's take Yahoo Finance, right? Same problem. Same problem here, right? So, we have a bunch of stories, and our goal is to pick the best from a pool of content, right? So the same problem, and the same methods apply to this kind of problem. Yahoo News, for instance, again, a bunch of news stories. In our case, we get these news stories from third-party sources. So we have a pool of stories in our inventory, editorially curated. And again, the goal is to pick the best story for a user visiting our portal. So same problem, right? Okay, right. Okay, so I already talked about it. So The most popular, so the first method which I'm going to talk about, selecting the best of the web, is going to be based on a combination of time series models coupled with what are called multi-armed bandits. So I'm going to talk briefly about why it is a multi-armed bandit problem, what is essentially a multi-armed bandit problem. And then I'm going to talk about personalization based on user covariates. This is again going to be based on logistic regression, very well-known data mining technique. But the difference would be it's going to be an online logistic regression. So it's not going to be something which you build per day and then you just use it for the rest of the day. That's not what would, that kind of methodology does not work very well in our scenario. Our online logistic regression has to be more dynamic. So we update our logistic regression every 5 minutes. So we get data every 5 minutes and then we update our models. And this quick adaptivity actually is key to success in the front page application, in other content optimization application. And then I'm going to talk about personalization. Again, this is going to be method based on extending matrix factorization kind of techniques. Okay. So I'm going to make some more assumptions in the talk just to keep the exposure simple. So I'm going to assume that we are going to optimize for a single slot. So I showed you 4 different slots, and optimizing for all the 4 slots simultaneously is a much difficult problem. It's a subset selection problem. Subset selection is difficult than just a single slot optimization, right? So for instance, if you already show a finance article, then showing a finance article in the second slot is not a good idea. Maybe you have very good articles. Both these finance articles are great, but if you have already shown one article and the second article is kind of correlated with what you what you have shown on the first slot, then it's probably not a good idea to put that into that slot. So slot optimization or subset selection is a much difficult problem compared to selecting articles for a single slot. So I'm going to talk about only single slot optimization in this talk. I'm also going to assume that the process of creating the inventory to choose from and the statistical models, they are decoupled. In general, that's not the case, right? If you know that people who visit the Yahoo front page from 10 to 11 on a Tuesday like more sports articles, then your inventory should kind of reflect that, right? You should actually have an inventory of more sports articles from 10 to 11 on a Tuesday. But in this talk, I'm going to assume that these 2 processes are decoupled. There are other effects that play an important role when we do recommendation of content, like user fatigue. So if a user comes in and if you show the same article to the user 10 different times, the click rate tends to go down. So we have studied these user fatigue effects in details in a www paper, but I'm not going to talk about that in this talk. But it is an important consideration. The click rates of users with more exposure does go down very sharply. In fact, similar observations have been made in a paper in 2008 where the authors studied content recommendation on the Digg website. So it's not something which we discovered first, but we also noticed the same kind of impact. Diversity in recommendation, how to ensure that you have enough diversity in what you recommend. Currently, we do it through business rules. We do it through editorial oversight. We just say, well, I'm not going to have more than 2 finance articles at the same time. But in general, it's a data mining problem. One ought to be able to formulate objective function that can incorporate both diversity, which is reflective of long-term, it is reflective of long-term user behavior. Right? So in general, when we're doing recommendation, our utility function should incorporate both long-term and short-term objectives and then do the recommendation. But again, I'm not going to talk about that here. I mean, that's a very challenging problem.
Sounds like a retail assortment planning problem in retail, like figure out what's the assortment you put on the shelf.
Right.
What's the variety.
Right.
And in some geographies, you offer more variety of liquid detergent and some less.
Yeah. And it has to do something with long-term user behavior, right? So yeah, the same problem here as well. But what are the right objective functions? Again, not the subject of this talk, but very important topic. It does come up a lot when you're running a real recommender systems. Maybe not while writing papers, but when you're running a real recommender system, it's very important. And sometimes those simple diversity rules can actually give you better performance than very complex models. It's very important. Yeah. Okay. So before I talk about the methodology, I want to just show you some data from our system. So everything in the data is real except the y-axis, and for obvious reasons. So the y-axis are scaled click-through rate of articles. So let me explain what each curve here means. So what we did was, so in our system we have a small fraction of visits where we randomly select a user. So for every single visit we flip a coin, and with probability 1% we just randomly send this user to what is called a random bucket, right? So in this bucket users, there is a 1% user visit that go randomly in this bucket, and for every visit in this random bucket we just randomly select 4 articles out of 30 and serve it. So this is so on 1% of our bucket we run a completely randomized experiment, no selection bias. If you look at serving data that is obtained, for instance, like the Netflix data which was in the competition, that data is something which is obtained from a serving scheme, where the goal of the serving scheme was to actually serve good articles to users. So there is inherent bias in this system. You'll always see good articles served in the first position, right? And you cannot get unbiased, you cannot study the system in an unbiased way by using such data. So what we did was very simple. We just took a small fraction of traffic where we randomly serve articles to users. And this data which I'm showing you is actually from that random bucket, right? So there is no selection bias in these data points. So now what is this data point? So this data point, each curve on this data point is an article. So for instance, this article was put into the system by the editors at this time point, and then this is the click-through rate of that article, and then at this point of time the editors decided they're going to take it off from the system. So each curve here represents an article lifetime and that CTR trajectory during the lifetime. And it is unbiased because it's from a randomized experiment. If you look,
the inventory that was created and curated was not random, right?
no, the inventory is something which was created by the editors, so it's not random.
So those 50 articles were probably better than most of the other articles on the web.
Right, so as I said, since this is the Yahoo front page, we have very strong policing kind of thing. We are very careful not to drive away any user at all. I mean, so we are very careful on the Yahoo front page at least to provide the best user experience.
So the reason I say that is because it's not completely random. There is at least some bias attached to it.
I think he's trying to say it's a selection bias in terms of the
Yes. So this does not address the selection bias of the content. Given the content that has been created by the editors, this is random. Yes, that's true. The colors don't signify anything. Those were just colors which automatically popped out of a visualization software. But yeah, they don't mean anything. Those are just to show you that there are a lot of articles running in the system over a period of 2 days. Right? And one thing to note here is articles have short lifetimes. During many periods, there are breaking news stories or some breaking stories. So the CTR of some of these stories, so like during this period, this story is clearly much better than the others. And you don't need a sophisticated algorithm to know that. I mean, just counting clicks and views will tell you this is a better story, right? So the statistical challenges are not that great during these time periods. But if you look at a time period like this, everything is very close to each other, and that's where you need good statistical model to figure out what is really a good article to choose and show on the. Yeah, this is all server time. That's right. So this is aggregated click rate. So we are not talking about any personalization over here. This is completely, in fact, the reason why you see temporal trend is partly due to that reason, because it's a mix of user population, right? Some of the click rate variation one sees depends on the kind of users visiting our website. So I'm going to talk about personalization in the next part of the talk, but yeah, this is everybody, right? Yeah, right. So this is the Yahoo US portal, but it also gets visits from foreign countries. Foreigners are also very interested in US culture, and that's known, right? But yeah, it is predominantly US traffic. Yeah.
About how many users would typically be associated with each of those curves?
So this is, okay, so I'm going to quote ComScore numbers, okay? We get 200 million visits according to ComScore on the Yahoo front page. Not 200, sorry, 110 million something on the Yahoo front page every day. And this is a small fraction of that, 1%. And every point here is a 5-minute interval, right? So you can do the math. I think it's approximately 5,000. Okay. So these are some of the statistical issues in choosing the best of the web for this data. First, there is temporal variation in article click rates, right? So if your goal was just to choose the best of the web, no personalization. Let's say your module demands that, okay, I just want to choose the best of the web. I don't want to choose different articles for different users. This is one big issue, right? There is the article click rates are not stationary. They're non-stationary. So you have to incorporate the non-stationarity into your models. Short article lifetime. So quick reaction, very important. If there is a Michael Jackson story, you want to know it's a good story in 5 minutes. You can't wait for 1.5 hour. Half hour is eternity on the web in the context of this application. And users in this area are very unforgiving, right? I mean, if they get too bad experience, I'm not going to Yahoo. I'm going to go to Google. That's it. So we have to be careful, right? So breaking news stories, you have to detect it very quickly. Cold start, right? So if there is a new article coming into the system, how do you learn the click rate of those new articles rapidly, right? That's another issue. So this is the approach. So in order to incorporate the non-stationarity, we use standard time series models. I'm going to explain what models we use. And then in order to incorporate the cold start problem, we do what is called multi-arm bandit in the literature. So if you have a new article coming in, the question is how much should I invest in this article? This is a new article, it may be very good, like what you do in stocks. Well, it's different from stock. In stocks, you are actually more concerned about being risk averse. Here, risk averse is not a main concern. Right? So if there's a new article coming into the system, how much should I invest in this article now so that if it is good, I actually can detect it as quickly as possible. So that's really roughly the multi-arm bandit problem. Okay, so I'm going to describe,
In like web page design or banner design, there's A/B testing. Do you do any kind of A/B testing? Like, do we show a finance article that's kind of written like USA Today, or more of a technical one that's like something out of a Wall Street Journal?
Yeah.
Where one of the features might be the writing level.
Right. Through this multi-arm bandit design, you can think of the multi-arm bandit design as doing a continuous A/B kind of tests. But these A/B tests are not equal sample sized, right? So the A/B test, we kind of make sure that the A bucket and the B bucket, they get completely randomized traffic. And the reason why that is done is that's the best way to maximize power. When you're detecting some small statistical difference, the best way to maximize power is to run a randomized A/B experiment. Here what we are doing is we are doing a sequential experiment. So for instance, if we figure out that this article seems to be promising, we are going to skew our probability of allocation and start serving that more than the other one. So this loses power, but it increases the overall click rates. So that's really the main difference here. So this can be thought of as a continuous A/B experiment, but more adaptive instead of the traditional A/B experiment. But in order to test two different algorithms, we have to do A/B test. So that we always do, right? Like for instance, to convince the editors, it was not very easy. So to convince the editors that this machine learning should be used to place content, we had to do A/B test and conclusively prove that it is better than using subjective human knowledge. So there we do A/B test. But this is actually an A/B test kind of thing, but more adaptive. Okay, so maybe I'll not go through too much detail here. They are all in the papers, but I'll just explain. Okay, so let's say you want to track an article click rates over time, right? So this is a standard time series model. And the first thing which will come to mind is, let's do an exponentially weighted moving average, right? So the exponentially weighted moving average is going to say the CTR at time t plus 1 is a weighted average of CTR estimate we got at time t and the CTR which we have in this time interval for a given article. This is all for a given article, right? And if you expand this recursion, you get this. So this is like a exponentially decaying average of the CTRs over time, right? This is what you do. Turns out this doesn't work very well because the variances are not propagated properly. If you do an exponentially weighted decay of the CTRs, the variances don't propagate properly, and you get very bad performance. Yeah. N is the number of times that article was shown in that 5-minute interval. C is the number of clicks you obtained on that article in that given time interval. So if you just do an exponentially weighted moving average on the ratios, the variances are not propagated properly, and you get very bad performance. Well, bad performance.
Increase or decrease?
So the variances are proportional to the size of the click rates. And having a constant factor, decay factor, is not the right thing. The decay factor has to depend on the effect of the size. Right? So this formula doesn't work. So this seemed to work. All right. So what you do is you do a separate exponentially weighted average of the clicks and the visits. Right. So the number of clicks you get on a given article at time point t plus 1 is the total number of clicks you got on that article in this time interval, plus a decayed version of your estimate in the previous time interval. Right? So if you expand that this is like this is an exponentially weighted moving average of the number of clicks which you have obtained on that article from time 0, when the article came into the system, to up time t plus 1. You can do the same thing on the number of times the article was shown. And now if you take the ratio of these two things, that works very well. Right? So the lesson here is if you are tracking click rate over time in any application, don't do any exponentially weighted moving average of the ratios. Do an exponential weighted moving average of the clicks and the views separately, take the ratio. That's going to work better.
One more question. So I kind of assumed that you were going to do this on the 1%, leave out data, but you're not. Right? Because if you were, the n will probably be somewhat of a constant, right? Assuming it's, IID and stuff.
Not exactly, yeah, it is kind of constant, but still it varies.
So you're doing it on the 1% or you're doing it on the feedback of the recommender?
We are doing it on the 1% for this application.
Okay.
Right? But I'll show you when we do better sequential designs, then this random is going to become non-random. So this random.
Right, for sure.
Yes.
But on the 1%, it shouldn't make a big difference, right? Because if you draw randomly from.
Right, but if you do this on the 1%, it's still not going to work, because the CTR of some article, even in the random bucket, is going to be much smaller than the others, and so the adaptivity of those. So if there is an article with higher CTR, you should be more adaptive compared to an article that has lower CTR. So the adaptivity has to change depending on the click rate size. Right.
What's the time frame for you to take this 1% sample? You post the article first minutes, first 10 minutes, or first hour?
As soon as the article gets into the system.
Video, if you can repeat the questions.
Oh, okay, sure. So the question was, since this is done on 1% random traffic, these two things should pretty much give the same answer. And the answer is no, that is not the case, because the variances of this click rates depend on the size of the CTR. Right. Okay, so what I described was more like an algorithm, but why is that a good algorithm? So you can actually show that what the estimate which I got in the previous slide, it is actually coming from it's actually the posterior mean from a well-defined time series Bayesian model. Again, I'm not going to go into the details, you can read it in the paper, but if you write down a model which looks like this, so the number of clicks which you get at time t given the number of views is n of t, and this is the true CTR. If this is the Poisson, and then you can assume that the CTR evolve over time according to the state equation, where so at time t plus, the CTR at time t plus 1 is almost like the CTR at time t, but there is some evolution, right? I mean, that's why the system is adaptive. If there is no evolution, then the CTR is going to be stationary. So there is some evolution, and this distribution kind of defines how much evolution you need in the system, right? So if you have this is a Kalman filter. Once you have the Kalman filter, you can first write down the prior mean of the article at time t plus 1. So the prior mean at time t plus 1 is exactly equal to the posterior mean from the previous time point. The prior variance is the posterior variance from the previous time interval plus some innovation, which is coming due to the adaptivity. Right? So you have the prior at time t plus 1, you have the likelihood here, you combine them, you get the posterior mean, and you can show that the posterior mean which you get out of this model is exactly what I wrote in the previous slide. So the previous model has a theoretical way, you can derive the previous model from this particular Bayesian model, and that's why it makes sense. Right? The exponentially weighted moving average, you cannot derive it from things like that. Right? So, it does not. Okay, so this is again some data I'm showing just to show you that this is like, so these are real click rates, and this is what the model estimates, right? So it's kind of tracking the CTRs pretty well. Well, that's what it's doing. Okay. Okay, so now let's go to the new article scenario. Okay, so if there are new articles in the system, or if there are articles where the click rate has very high variance, but lower mean, right? So maybe there is an article where the click rate estimate is 10%. Now there is another article where the click rate is 5%, but very high variance. What should we do, right? How do we learn about the quality of a high variance article without incurring a very high cost? Right? That's really the main problem. So if you are slow to react, as I said, it can be a bad thing. If there is an article which is very good and if you are slow to react, to pick it up, then it's going to hurt our performance. If you are too aggressive, then we may show a very bad article to a large front page population in the first 10 minutes. So we have to decide what's the optimal trade-off, right? So just to understand the trade-off, let's say there are 2 articles in the pool. Article 1 has a CTR of 2 in 100. Article 2 has a CTR of 25 in 1000. So which one would you show? This one, right? But is this the best thing to do? It's not clear, right? Because this CTR is based on only 100 samples. It has higher variance. So there is a potential that this article could be much better than this article, right? So if you just get stuck in this local minimum and just keep showing this article, this might be a very good article, but the fact that you just serendipitously got only 2 clicks instead of 3 clicks in the first 100 shows takes it away from the recommendation completely, right? So that's not a good thing, right? So we have to have a best what is called explore exploit strategy. Explore the articles that don't look very good but have high variance. They might be very good. And once you do the exploration, figure out what are good articles and exploit that, right? So that's why it's called the explore exploit. So generally what it involves is, instead of taking a decision based on the estimates you have right now, you look ahead into the future, right? So don't think that your game is going to end in the next interval. Just say, okay, well, my game is going to last for another 4 intervals, and based on whatever I know now, what would be the performance of my system if I look ahead 2 time intervals or 3 time intervals, and do the calculation, come up with a gain function by looking ahead for the next 2 or 3 time intervals, and then make a decision. Right? That's what the multi-arm bandit literature does. So there's a huge literature on this. I'm not going to go through the literature here, but that's exactly what the multi-arm bandit would do. Yeah. Okay, so again, a lot of details not explained. So we took historic logs and did a very rigorous empirical data analysis to see whether the Poisson assumption is well supported by the data. And it turns out it is. And again, the details are all in one of our dub papers, where we kind of show through quantile plots that the quantiles of the Poisson we have matches the empirical quantiles of click rates which we get from the system. Okay, so if the click rate is based on only 100 displays of an article, then you are more uncertain about what the click rate is, right? If I just show you an article 10 times and if you click on it 1, then okay, the estimate of click rate is 1 in 10, but you're less certain about it, right? So 1 in 10 is more, so a CTR which is based on 10 displays and 1 click is more uncertain than a CTR which is based on 100 displays and 10 clicks, right? That's exactly what it is, right? So both of them have the same click rate, but the first one is based on a sample size of 10, the other one is based on a sample size of 100. So you're more sure about the sample size, you're more sure about the second estimate that's based on a sample size of 100 instead of. Yeah, right. Both of them have the same mean, or maybe this one actually has a lower mean than this, but you're more certain about this, right? So if you look at the distribution of that, this is the entire probability mass is concentrated in a very small range. Whereas for this one, the probability mass is probably concentrated in a bigger range. Right? So there is a probability that this article is actually better than this article. Right? So you can compute the probability of the CTR of this article to be higher than this article, and it's actually a non-zero number. Okay. Okay, so again, these are the so I'm going to describe the technical detail of the multi-arm bandit scheme. So again, I'm not going to go through all the technical details, but let me just try to give an intuition of what is the main underlying idea behind the explore exploit scheme, right? So in order to understand the explore exploit scheme, imagine you only have 2 articles in your system, just 2, right? And imagine one of them has 0 variance, So there is one article which we have shown on the front page a large number of times, and you know exactly what the click rate is, and there is no variance, right? Maybe it's based on millions of page views, right? So there is no variance. You know exactly what the CTR is. So this is what this article is, right? So there is one article which has a CTR of Q0 in the next 5-minute interval and a CTR of Q1 in the subsequent 5-minute interval. Right? So instead of just looking at the next 5-minute interval, which is what we are going to do in a traditional time series model, we are now looking at 2 steps. What is the CTR in the next interval, and what is the CTR in the subsequent interval, right? So let's say this article has a CTR of Q0 and Q1 in the next 2 time intervals. And then there is another article which you are not too sure about, right? So the CTR of this article, based on all the data I have about this article, is given by a probability distribution, which is, say, some gamma, right? Think of this gamma as just some probability distribution, some shape describing the uncertainty you have about the probability estimate. So now the goal, so if we just go by the myopic rule, right? So if the expected value of this is less than this, and if you just go by the myopic rule, you're never going to show this article, right? Okay, this CTR is less than this CTR, I'm never going to show that, right? So that's a bad strategy. We should not do that. Right? That's the 2 in 100 and 25 in 1,000 example. We don't want to do that. What we really want to do is, we want to say, okay, well, this is based on 100 views, so maybe there is a lot of variance, and there is a chance it may be actually much better than the article where I have a lot of data. So let me do something. Let me decide how many times I'm going to show this article in the next 5 interval. Right? So in the next 5 interval, I'm going to get 5,000 visits. Maybe I can allocate 100 visits to this article, which looks promising, but it is not the best in terms of the mean estimate, right? So this is what you need to decide. This is what the optimization algorithm has to decide. How many times should I show this suboptimal article in the next time interval? If I'm going to get 5,000 views, should I show this suboptimal article based on my current estimate 100 times, 200 times, 300 times? That's really what you want to decide. This is what this X is. Fraction of times you're going to show article 1 in the next time interval. And the calculation has to be based by looking ahead 2 intervals, because you're looking into the future. So you say, okay, well, if I show this article this many times in the next time interval, I'm going to get C clicks, right? So C is hypothetical. If I show this article this many number of times, I'm going to get this many number of clicks. And I know my model is Poisson, so okay, I know I can quantify the statistical uncertainty in the number of hypothetical clicks I'm going to get in the next time interval, right? Once I get this number of hypothetical clicks, I can update my distribution which I start with to this. So I start with alpha number of pseudo clicks, gamma number of pseudo views. If I get C number of hypothetical clicks by showing this article so many times, this is what my distribution is going to become, right? So my distribution is this. Once I get C number of hypothetical clicks, and by showing the article so many number of times, my distribution is going to change, right? Maybe it's going to change this way, no, right? Okay, so once I have my updated distribution in the next time interval, then I say, okay, well, now I only have one more interval left. So based on my updated distribution, I'm going to show this article in the subsequent interval if the mean of this article after getting updated is bigger than the mean of the certain article, right? This is really the logic, right? And so all these decisions are based on this number C and X. C is random. X is not random. X is something which we want to optimize over, but C is random, right? So we have to come up with a objective function which is obtained by integrating out the effect of C, right? And get a pure function of X, right? Yeah.
So you are placing yourself in the future, but why is it that one of the two why do you treat the two sides of the problem differently? It seems like you're taking one of them and say, okay, I know for sure what your variance will be in the future, and the other one you try to...
The other one I'm assuming is completely known. The variance is 0. And you'll see the reason why we do that. Yeah. This is a usual trick employed in multi-armed bandits. Right. Okay. So if you integrate out the effect of C, you get a gain function which looks like this. And this gain function, again, is a function of X and the CTR of the known article in the 2 intervals. And in fact, so this is the gain which you will get if you had shown the best current article in both the intervals. And this is the additional gain which you get by showing the uncertain article a certain fraction of time in the next interval. And this gain function is not negative, it is actually positive for a large values, for range of x values, right? In fact, we can visualize this is the objective, this is what the objective function looks like. So on the x-axis we have what is called the sample size. Right? Higher sample size means lower variation, and lower sample size means higher variation. So you can see that the fraction of times we will allocate this uncertain article in the next interval is a function of variance, right? So if the variance is too high, then the policy is kind of a bit circumspect. It says, okay, well, I'm going to allocate this guy, but not that many number of times. Once the variance reaches some threshold here, it says, okay, well, I'm going to show it too many times, and then it says, okay, well, now if the variance is very low, then of course you know equally well about both the articles, and then you should take the decision which you take in a myopic scheme, right? So this is what the function looks like, and the goal here is to find a value of x which optimizes this function, right? So this is about the two article case. Now you can generalize this calculation when you have k articles. This involves some mathematics. The mathematics was first formulated by Peter Whittle in a 1983 paper. It's based on something called Lagrange relaxation. So this I cannot cover it here. It might take another hour, but I'm just going to state that it is something which was done by Peter Whittle in the 80s, and we borrowed his ideas and kind of adapted it to our scenario, and that's how it works, right? So the two article calculation is extremely important. You can use that two article calculation and generalize it to the k article case. I know I'm being vague here, but that's how the whole multi-arm bandit theory works. If you have a k-dimensional optimization problem, you can actually get the optimal solution by solving k one-dimensional optimization problem. So that was a breakthrough result in the 70s and 80s, and that's what we're using here. Yeah.
Question. There's a famous paper by Lai and Robbins in '85 that says that under ideal conditions, with everything being independent and identically distributed and stuff like that, the best strategy is to go with mean plus variance.
Yes. Mean plus some k times standard deviation. Yes.
So across standard deviation. So if you went with mean plus something times standard deviation, would that give, how much better is what you're doing over that?
Yeah, so the answer is in this slide. So the mean plus standard deviation is what is called the UCB scheme in that literature. And I'm going to show you how better this scheme is compared to that. Again, I did not go through that scheme because of lack of time, but in the paper we have a rigorous comparison with what we have done with all the Lai schemes in the literature. And the Lai schemes are not it does not work as well here for several reasons. Number one, the click rates are not stationary. They assume the click rates are stationary. Number two, they assume feedback is obtained instantaneously. In our case, if you show an article, the user might be drinking coffee, and then he might click on the article 5 minutes. So we just can't conclude that the user is not going to like the article just by showing the article and after a second. So we have to wait for a few minutes and see what the user does before we conclude that he's not going to like the article. So we have to deal with this delayed response feedback, and this is something which was not built into this Lai policy. And the most important thing, those policies assume that the set of articles you have in the pool is static over time. This is definitely not the case in our scenario, because editors can put in new articles, they can take out new articles, and so that theory of multi-arm bandit based on Lai's calculation, that breaks down the scenario. Oh, well, because they think, yeah, so the question was, why would editors take out articles? So as I said at the very beginning, we don't believe at Yahoo that click rate is the only thing that actually is optimal for recommendation, right? Otherwise, we'll keep the Britney Spears article there forever, right? So at some point of time, editors say, well, no, there is a new news article that has come in the web, and I should take away this Britney Spears article and stop the statistical algorithm from recommending this to anyone that comes to our portal.
So earlier in the beginning you mentioned the talk is about also can be applied to other things like products and all that. Do you think that scenario actually replicates to other places as well? Like if I'm selling products and I want to show recommended products to a user, that would probably, thank you. if I'm selling products and I want to show recommended products to a user, then those product listings may not change that often. So my question is, would this model actually apply?
Yes, it will
even
apply.
if even if this pool doesn't
Change too much, yeah,
Yeah.
it will apply. In fact, it will start doing much better. In fact, the scheme which we were talking about here, the UCB scheme, they will actually start. The gap is going to start closing between this scheme and the traditional multi-arm banded scheme that are there in the literature. So this scheme starts working much better when the pool is more dynamic, the CTRs are changing over time, but it will still apply. Okay, so this is some results. How much time do I have? There.
It's 8:05. You want to go 8:30, 8:45?
Okay. I just want to, because it's good that it's interactive, but also want to keep track of the time. Okay, so these are results from a test which we conducted on the Yahoo front page. I'm just showing you some results. This is now running live, so everywhere on Yahoo where we want to track most popular, best of the web on any portal on Yahoo, we use this scheme. But I'm just trying to show you the qualitative and the quantitative aspects of this scheme based on some small experiments which we did on the Yahoo front page. So what we did was, on the Yahoo front page, we took a small fraction of traffic, and in 15% of that traffic, we ran different explore exploit schemes, right? So base 2x2 is what I talked about. Then there is something called UCB1 in the literature, which is widely used. That's the scheme. In fact, we did not use the UCB1 directly from the literature. We had to do some modification to incorporate delayed feedback. But again, those are minor. I'm not going to talk about that. But some modified variation of UCB1. And then the epsilon greedy. So epsilon greedy is what I talked about in the beginning. With probability epsilon, you just serve an article at random, and with probability 1 minus epsilon, you look at your estimates and choose the best one. That's called epsilon greedy. So the bold line here represents the overall CTR which we got in this 85% bucket. So in 85% of the traffic, at any given point of time, we serve the best article depending on the CTR estimate, right? So why did we do it this way? We wanted to detect the false positive and false negative rate of different algorithms, right? So an algorithm that performs worse in this 85% of the bucket means it's too aggressive. It kind of just picks up the wrong article more often than an algorithm that has higher CTR over here. In the 15% sample, if the CTR is very high, that would mean that that particular multi-arm bandit scheme did a great job of exploring exactly the right article and converging to the best, right? So if you look at the bold lines, there isn't too much difference, right? But the dotted line is where you can see the difference, qualitative difference in these schemes, right? So the epsilon greedy is this green line, and it is no surprise that the CTR of the epsilon greedy is the lowest, right? Because you just randomly explore things, right? I mean, you don't do anything intelligent at all. The red one is what is the UCB scheme. This is what is used traditionally in the literature. And the black one is the Bayesian scheme, which I talked about. In fact, it is very close to what you see in the optimal bucket. So it is able to converge to a very good article very quickly by just looking at by just doing a few experiments, sequential experiments, on some articles. It is able to figure out, oh, this is bad, this is good. And much of the behavior of this has to do with the optimization function I showed you. So when an article just comes into the system and there is a huge variation, it actually is a bit cautious. It does not start exploring it immediately, which is what epsilon greedy and UCB will do. Every time it sees a very high variance article, it will start exploring it very aggressively, and then it will, oh, no, it's not good, then it's going to take it out. But this scheme does it in a much smoother way. If the variance is very high, it starts slow, and then it ramps up. And that is really a key ingredient which makes it work better. So this also shows you that the initial priors which you start with are very important. Right? So if, for instance, if you have some additional domain knowledge about the article CTR and you can fold it into this scheme, then the initial CTR priors which you begin with would be narrower, and the convergence is going to be much faster.
So you can incorporate
Absolutely.
domain knowledge.
Yes, that's the beauty of all the Bayesian models, right? I mean, you have any prior estimate, you can incorporate that, and you're going to expedite your convergence. So one problem with most of the multi-arm bandit schemes in literature is most of the results are asymptotics. But we know in industry we can't live with asymptotics, right? I mean, it's really so if you really have domain knowledge and incorporate that into your model, the convergence is much faster, and your performance will be much better.
You, for instance, a follow-on to say that this article is an extension of a previous article
That's a very good point. Yes, you can actually just do a random walk. Okay, well, this article left the system 3 hours ago, and the editor has just incrementally posted another article which is very similar to that. Maybe there's a follow-up Michael Jackson story. You can actually borrow information from that and seed this new article, and you'll have much tighter prior here. And that's going to speed up the convergence, right?
The next volcano story.
Yeah, that's right, yeah. Okay, so this was all about, yeah.
So, can't this have a problem with timing effects? So, for example, you see an article, it comes in your inventory, but somehow people start responding to the article only 2 hours later, and the article lasts for 6 hours. So, your first 2 hours worth of data will give you a very low, and you'll have a high enough variance that you might discard the article.
So why do you think that would be the case? Like, why would users not respond to it?
For whatever reason, maybe like it's connected to the story breaks throughout the rest of the web maybe later or something like that.
Well, then they should click on it more, I guess, right? I mean, if we are detecting the breaking news story first, then I guess the user should be even more excited. I mean, the problem is if it has already broken somewhere else and we are late in reacting to it, like what happened in the Hudson case, the Hudson airplane story. I mean, the editors detected it like half an hour late compared to the other parts of this. So there, actually, the click rate was much lower than it should have been. Right? So the problem is opposite. So in fact, that's a very challenging problem for editors to keep track of all the breaking news stories and put it in the pool as quickly as possible. The question, so they have to do all this window dressing. I think that's the thing which they have to make sure the pictures and images and the text look all nice, teasy, so that users click on it and go to the appropriate page.
And also because you have the human editors in the process, you have feedback, so I don't think that will happen.
Yeah. So the human editors would figure out that's not the case. Yeah.
Do you do anything special in picking the article with the zero variance? Just pick the article that had the lowest variance.
Yeah. So the zero variance thing was only for the explanation of the algorithm. In general, we don't have any zero variance article. This was just to define, just to explain the algorithm. And in fact, some of the calculations, when we are doing the calculations, it turns out that we have to measure performance of every article with respect to a hypothetical zero variance calculation. So if you do the Lagrange calculation says, okay, compare every article with a hypothetical zero variance article and then select the best. So that's more for mathematical calculations rather than reality. In reality, none of the articles are assumed to have zero variance at all. Okay, so I guess I'll just move a little fast. We'll be a little out of time. So now I'm going to talk about personalization based on user features, right? So again, this is the typical Netflix kind of problem, right? You have users coming in, you have items chosen from the inventory. Items may have some features like keywords, content categories. Users have features in our case. So we know the user demographics, we know user browse history as I talked about. And now the goal is select items to show to users. Every time you show an article to a user, you get some response, which is a click or a no click. And now the goal is, as you keep getting more and more data on this matrix, how do you learn the click rates and provide the best possible recommendation, right? So that's really the problem. So again, this is the most natural model we would all write down as data miners and modelers. So this is the response of the ith user on article J at time t, and we'll assume that it is coming from some Bernoulli model with this probability of click, and the log odds of the probability is again, so this is the usual logistic regression. The log odds of the probability is a linear function of features. You take all the user features, you take all the item features, do all the cross product, put it in, right? This is the kitchen sink model. I call it the kitchen sink model, right? Put everything in the kitchen sink and see what sticks, right? This is the kitchen sink model. Now this is the important model. So this is all the kitchen sink model, but the kitchen sink model is not able to account for a variation in items of the same kind. So if you take two different finance articles, the way they interact with the same kind of users are very different, right? So finance article, maybe both of them are finance, but one of them might be about GM bailout, the other might be about I don't know, something, right? I forgot about my finance stores, but yeah. So two different articles, both of them from finance, may have very different behavior in terms of how they interact with the user's tastes, right? So this part here, So this vector over here, so if there are 1,000 different user features, this vector here learns 1,000 item coefficients for every single item. So every single article, we learn 1,000 different weights when it comes online. And so the challenging part here is we have to learn it online, and we have to learn it quickly. If an article comes and if we take 30 minutes to learn these 1,000 parameters, then we are doomed. We're not going to be able to do a good job. Unless this part, the kitchen sink part, is really good, which is usually not the case. Well, it can be good, then we have to spend a lot of effort doing feature engineering, which may or may not happen for applications. Yeah. So the article affinity to a user segment may also change over time. Right? I mean, there might be temporal variations in the article click rates to a given user segment. So article CTR for a male segment from California interested in BT finance can change over time. Right? So it is not very difficult to incorporate time here at all. So we just put it in, right? Yeah.
So but you're not extracting new features from the new articles?
No. Yeah, so whenever a new article comes in, we have this features xj. And okay, this is the prediction from the kitchen sink model, but this is not explaining the behavior of this article. So we learned this additional modifier. And together, so the reason this is helpful is it helps you converge faster. If the kitchen sink model has already incorporated all the variation, then these numbers would be very close to 0, and they will not contribute at all. Right. Okay, so in order to reduce the dimension, we take recourse to a very old technique in statistics called reduced rank regression. The first paper was in 1954, and then there was no work for 60 years. And then the second paper appeared in 2001. Well, no, that's not right. There are many other papers studying theoretical aspects of this problem, but the practical application came in the next paper. So the main idea here is you take all your weight vectors of items and you do a decomposition. You say, okay, I can do a lower dimensional decomposition of the weight vectors. Right? So let's say I have 10,000 articles. Each of them have 1,000 coefficients. Now you say, okay, well, I don't have to learn 1,000 parameters for all these items. There is some commonality in the weights across these items. Right? And this common factor is given by this vector b, and the only thing which I have to learn online is this additional factor theta. Right? So maybe this is going to make it more clear. So we write the v vector for every article as a product of a global matrix b times a online modifier which you have to learn for every single item when it comes online. So this b matrix is actually learned based on all the offline analysis. So I have all the log data in the world. I can just go and look at my log data and learn exactly what this B matrix should be. Right? You don't need any metadata at all. You just need item level data, and you can still learn the B. Once you have learned the B, then when an item comes online, all we have to do is just learn this theta, which is like 5 or 10 different parameters, and that's very easy to learn. Right? So this is like principal component, right? I mean, you could have also done a principal component of the user features. Right? So instead of having 1,000 features, you could have just done a principal component of this and reduced it to 5 linear combinations. But the advantage of this is you're learning this linear combination based on the click data itself. You're not doing unsupervised principal component. Right? Right. So again, I'm going to show you some results here. So this model here is the saturated logistic regression. So we don't do any dimension reduction. We just try to learn all the 1,000 parameters online. Right? Forget about this. This is just the kitchen sink model. No online modification at all. This is our baseline. Right? Just the kitchen sink model. This is the principal component regression model. PCRs are 2 different variations of take the user feature and just do a principal component regression. Don't use the click data in learning a lower dimensional projection at all. And this is the model which learns the regression component by using the reduced rank regression. And as you can see, the reduced rank regression tends to do much better compared to other methods. Right? So this is test log likelihood over time. Right? So we just predict the test log likelihood in the next 5 interval, update our model, test log likelihood in the next time interval, and so on and so forth. And the results are significantly better if you used a reduced rank regression compared to not using a reduced rank. PLS, partial least square, it is. Partial least square actually tries to optimize the canonical correlation. So this is like that, but the main important thing here is the online aspect. Partial, again, there are many techniques in the literature that do these things offline. But so the first thing is it is binary data. The number 2 thing is it is incomplete matrix. The number 3 thing is we are using it to do online online learning. We are expediting online learning by using this concept. I think that's really the main novel concept. I'm not saying we are inventing reduced rank here. No. We're just using the ideas to expedite online learning for collaborative filtering application, and you can use this technique without collecting any metadata. You can just, if you have historical logs on items, you can still use this technique. No metadata required.
So you're including the new articles in the training set.
Yeah.
And how are you deciding which class they belong to?
Well, when a new article comes in, I will know so you're talking about this one here? Yeah, so this I will know. When a new article comes in, I will know the finance. This I have already learned from offline data. This is a global number. And this theta is what I learn online. So I show this online. I show the new article in this random traffic. I get feedback and I learn the thetas online. Right? But I have to learn only 5 parameters, so it's much faster. Right?
So when you say you go to the next slide. Oh yeah. So when you say you have 1,000 parameters, that's the size of your vector.
Yes. Size of the vector x. Yes. Yes. Yeah, we end up learning 5 online. Yes. Yeah. Okay. So do I have 10 minutes or? Okay. 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 So this is so now I'm going to get into the Netflix kind of problem, right? So far we were assuming that the users have covariates and we are learning per item models. Now let's consider a generic model where we have to learn user vectors and item vectors both. Right? So this is exactly the Netflix kind of model. Well, not one of the Netflix model, which was successful. Right? So you have ratings of user I on item j, and the model is basically made up of 3 components. Well, there is a global mean as well, but let's forget about that. So the probability of a click, the log odds of a probability of a click of an article j on user I is made up of user popularity, item popularity, and then there is a term which captures the interaction or the taste a user has on that given item. And how do we capture that? We take every user, we project them into a latent space of R dimensions, right? So every dimension of this space represents one aspect of a user's taste for content. We do the same thing for every content item, and then we say, okay, let's take the cosine of the angle between these 2 vectors, and that's going to capture how much a user likes a given item. Right? So this is the Netflix model. It's called matrix factorization as well. Now notice writing this model. So this model is extremely flexible. So this model as such doesn't mean anything at all. Right? Why? I'll tell you why. So if there are n users and m items, this is the total number of parameters you have in this model. Given that our matrices are highly incomplete, we only get data on 1% or 0.5% of the cells in such application. Even for small values of R, this will start overfitting if you don't put any constraints on these guys. You have to constrain these guys in some way, right? So so the key technical issue in fitting these models is how we constrain the values of these parameters. This is also called regularization in machine learning. It is called priors in statistics, whatever you call it, but you have to put some constraints on these parameters. And the usual approach which have been used in Netflix is to assume that these come from a zero mean Gaussian prior. So you're doing a ridge regression on both the UIs and the VJs in the Netflix concept, in the Netflix application, and again they have been shown to work pretty successfully on the Netflix application. So if you write down a generative model, you can write it this way. You can say, okay, these alpha i's are coming from some Gaussian distribution centered around 0 with some width a alpha. Similarly, these are centered around 0 with some width a beta. Each of these vectors are again coming from an R-dimensional sphere centered around 0 with some ellipsoid a of u. So this is again another ellipsoid. And the fitting procedure estimates all these a alphas, a betas, a u, and a v's, and then given these estimates, you can predict for a new. You can predict a rating for a new article for a given user, and so that's exactly what the Netflix model does. Okay, so now so this is not going to work in cold start. Let's say there is a user who comes to our website and you've never seen that. So if you use the previous model, you're going to say, okay, well, the factor estimate of this guy is 0 because I've never seen him before. But in our case, we have more information. If we have a new user and if we know that he's interested in finance versus another new user who's interested in sports, well, I should have different priors for finance and sports, right? So the finance guys should belong to a different sphere compared to the sports guys. They should not be all clubbed into the same sphere, which is done in Netflix, for instance, because there is no metadata. At least in the competition, there is no metadata. I'm sure you have a lot of metadata. Okay, so this is again a very general model I wrote. In practice, we have tried estimating the entire covariance matrix AU, and we have also assumed that this matrix is diagonal. They make no difference. In fact, the diagonal models seem to work better. So I would recommend not trying out any fancy variation of this model. Just stick to diagonal covariance matrix, and it does fantastic. No reason to do rotations and all that stuff on the factors. Right? But in general, this is how you will write it out, right? I mean, you just say, okay, well, it can, the UIs may not be orthogonal, so there might be some correlations. I'm going to estimate the correlations as well. But there's no reason to estimate the optimal correlations among these factors. Just assume they are independent, and you will be fine when you're doing the estimation, right? Okay. So that's the main idea here. So we should not shrink everyone towards 0. If we know that this guy is from California, so the Californian guys should have their own priors. The BT Finance guys should have their own priors. The females from New York should have their own priors. Everybody should have their own priors. And when you don't have enough data about a user, you should actually fall back on the appropriate prior rather than falling back on the 0 priors, right? So this is exactly what we do, right? Instead of assuming that we are centered around 0 mean, we assume that we are centered around a regression function, right? So if there is a user I and these are the covariate vector of the user I, we learn a regression function around which we want to center the priors, right? We do the same thing for all the factors as well, right? So we learn this parameter G, right? So every factor here has a separate regression function. If there are R factors, you're going to learn R different regression functions, right? And this is going to help you center people in around different priors, and it kind of provides you a unified solution for both the cold start and warm start situations.
And so the regression function you get from the metadata, is that what you're implying?
Yeah, so these are all metadata. These are all available. These we learn. We learn from the model itself. So the estimation technology is going to learn both these G's and D's and AU and AV and A alpha and A beta.
Right, those are not dependent on the metadata. Those are dependent on the user.
Yeah, this is dependent on the metadata.
That's dependent on the
Yeah, and we are going to learn this G0, D0, G, and D. These are unknown weights. We're going to learn it. And we can learn it.
If you have a new user, you don't have their click history. So what do you use for priors?
Oh, we use this, right? So we don't, if you have a new user and you are interested in finance, we don't have your click history, right, but we have the click history of everyone who was interested in BT Finance, right?
Okay, so after they come to the first chart,
yes. Yeah. So it's okay, well, this guy is interested in BT Finance. I've not seen his behavior, but I've seen everyone else who is interested in BT Finance, and their factor estimate is exactly this quantity. So you are going to borrow this factor, at least for the time being. Once you start giving us more clicks, then we're going to move away from that. And this is better than just saying, okay, you have 0 priors, right? So that's what I'm saying. Right? Okay, so these are just details. You can do this model fitting by using an MC-EM algorithm, right? So we run an EM algorithm, but we do MC-MC. It turns out if you do MC-MC, the performance is much better than if you do something like gradient descent. Right? But this is just more a technical point than anything else.
Performance, you mean computational performance or effectiveness?
The predictive. Computation is a little more if you do MC-MC, 2 times more. Okay. These are all details. So we have, in the paper, we describe all the results. I'm not going to probably go through it just for the interest of time. Maybe there might be more interesting questions. But yeah, if you just trust me, this method seemed to work much better compared to other cold start methods we have compared in the literature. Like we have compared these methods like FilterBot. We are calling our method RLFM, regression-based latent factor model. This is the Netflix model. This is the FilterBot. There are many other variations in collaborative filtering we tried, like similarity-based methods, and at least on the benchmark data set and also on our data set, this seemed to work the best. So incorporating both the metadata as well as ratings seem to work well if you have a cold start problem, both cold start and warm start problem. In Netflix, it will not make a big difference because the test data has users and movies that are already well covered in the training data. So there it doesn't make a lot of difference. But if there was Netflix too, then it will make a difference. So by collaborative filtering, I mean the traditional collaborative filtering method based on Pearson's correlations and other similarity measures like based on clicks. Jacquard coefficient, Pearson's correlation, cosine similarity, the Amazon kind of methods published in 2006 in IEEE. Right, that's not the matrix factor. I'm calling out matrix factorization separately. Those are modern collaborative filtering methods, probably. Okay, so these are again results on this model on front page data. Again, these are all good. So I'm going to, since we are quite out of time, I'm going to just summarize what we talked about today, and we can maybe talk more offline or on email. So first of all, I would like to stress the simple statistical model, when coupled with fast sequential learning in near real time, seems to produce very good results for a web application. So you can take simple model, but update it very frequently in real time. That really works wonders, instead of waiting for a day or something like that. Right? So having an infrastructure to update your models in real time is a good investment if you're doing recommender algorithms for web applications. Matrix factorization seems to provide the state-of-the-art recommender algorithms. Again, we also find the same thing in our applications. And again, we generalize this to include covariates as well, so that we can deal with both cold start and warm start in the same framework. We don't have to go to a different model for cold start and then come back to matrix factorization for warm start. We don't have to deal with arbitrary decision criteria when to switch to cold start and warm start. We can just unify into the same framework. There's no need to make these ad hoc decisions. Just run the same code and you'll get the answer. And we also talked about reducing the dimension of our covariate vectors when for fast online learning based on reduced rank regression. So that seemed to help quite a bit as well. So again, our system again is complex, but you can think of our system built of these 4 components. So we do a lot of offline modeling. We have a lot of log data at Yahoo, right? A lot of visits on the Yahoo front page. We do a lot of offline modeling to create new features to put into the kitchen sink model. Right? So for instance, we do regression, collaborative filtering, latent factor model. For many applications, we have a very large inventory, and we try to reduce that by using relevance-based measure. So for instance, we use simple IR kind of measures and say, okay, well, out of these 1 million articles, well, we don't have 1 million. Out of 300K articles, these 100K don't look good at all because the cosine similarity is like close to 0, so they're kind of useless. So we remove many of them and then create a small pool, and then we do this explore exploit, which I just talked about. We have online models to do time series models, and the online models and offline models, they are all coupled with this multi-armed explore exploit schemes. So I did not talk about explore exploit in the context of personalized model. That's another topic which we have been working on, but I did not touch on that in this talk. We can talk about that again offline, but there are a lot of issues when you start doing online explore exploit with personalized model, especially when the article pool is very large. It's a very challenging problem. There are still open problems in that area. Okay, and we did not talk about these things, as I said. So finally, just to conclude, we have a rich set of statistical problems that are key to recommender systems, and so the good thing is, so this talk was given to statisticians, so I was trying to make them feel good, but maybe this is not a very good pitch for this crowd. So statisticians like to estimate both the mean and variance, right? So if they say, well, if you're just predicting the mean, put it in a black box, go to machine learning, don't come to us. So since I was giving this talk to statisticians, I said, oh, well, we need both mean and variance. That's good news for you. So you should kind of get into the area, right? I mean, that's the main spirit. But yeah, seriously, we do need mean and variance estimates to solve these problems. Otherwise, we are not able to do good explore exploit. Explore exploit critically depends on getting both the mean and the variance estimates right? And we do a lot of designed experiments in our system, sequential, A/B, and all sorts of things. And again, I think if this problems excite you, then Yahoo perhaps is one of the best places. We have a rich set of applications. We have large traffic, and we have global traffic, not just US, throughout the whole. And in fact, Yahoo front page, which I talked about today, is the most visited content page on the planet. So the volume is extremely high. Right? So Okay, with that I'll end my talk. I'm sorry I went a bit over time, but hopefully it was useful. Oh, you mean we get a new article where the feature is, where we have an entirely new feature?
Right, new features, new keywords probably, or a new HTML pattern, or whatever you're using.
Yeah, I mean, I think you're asking a very specific question. I mean, there are several. First of all, I have not done that. I think we do some. We are in the process of doing that right now in the context of news and other application. But one option is to build separate models.
Asking, do you think that would matter?
No, that would not matter. As long as you have a good offline model, it should be fine. Right? At least the framework should not matter. Of course, like if you have a very important feature, it could matter a hell lot. Right? I mean, one good feature can completely change the whole system. But that is more application specific. But in principle, it should not matter. Yeah. Yeah.
How do you come up with the covariates? They're essentially, so the fine-grainedness of them would directly affect the priors. And
Absolutely.
so did you guys, so for you, it was probably like really obvious in the sense that gender, age, so the kind of information you have, you will have covariance according to that so that you can actually get reliable estimates for the, but like did you guys do some kind of an experiment where number and type of varying the number and type of covariates made difference, because it would, so you guys are doing the for personalized recommendation, you have really good priors, right? But changing the covariates would change the priors. And
Yes. So what we did was we did a lot of offline analysis, as we do usually in data mining, and did a feature selection. Right. So we started out with a bunch of with lot more features than what I said. Like we had 1,000 features, but when we began with like 100K features. But we did the usual variable selection, which we do in data mining. Again, I can talk about that. We did something based on Kullback-Leibler kind of mutual entropy kind of measures and narrowed it down to 1,000 important covariates. So this is the usual feature selection paradigm which we have in data mining. It is slightly different in this context because we have this matrix data, so we can do a much better job. Like for every feature, I can compute a Kullback-Leibler distance between how that feature interacts with all the items versus what. So the baseline for the Kullback-Leibler is a uniform distribution, and then we select the best one.
another issue, so like as you said, typically you have like really sparse matrix. So for some users, so how do you decide that for this user we can way more collaborative, we can have more weight for the offline thing and like less weight for the online?
So this is all decided by the model, right? So the beauty of that model is you write down that whole equation, you write down the likelihood, you train it, it automatically decides what should be the weight. You don't have to tweak the weights at all, right? So that's how it is. I think that so that's why you have to solve this expensive EM algorithm, right? I mean, otherwise there won't be any benefit to doing that. Yes.
So one of the stats you had was on false positives. What's a false positive for you?
False positive is if there is an article which is not truly good, but we pick it up early. So let's say there is an article which is not really good, but I run an explore-exploit scheme, and that explore-exploit scheme picks up a wrong article. It will recover eventually, but I lost 10 minutes showing a bad article to the user. So that's false positive for me.
The badness is calculated by the hit rate.
Yes. How much clicks did I lose because I showed this article? Right now, yes, but in general, it could be a more complex function. Yeah. Any other questions?
So, one question. I mean, you earlier in the talk you said about the subset where you said this was limited to the selecting one good. Earlier in the talk you talked about that it was about one slot that you're trying to optimize for. So just some high-level thoughts on if there are multiple slots. The challenge goes that even if CTR, I don't know how good a CTR is a predictor, because somebody is clicking on a really good article, in one of those other slots. What happens to the articles in the other three?
Yes.
So do you have any high-level ideas of how to deal with that?
Yeah, so we are looking into this problem using things like multinomial logistic regression. So this is, for instance, some of this technique, for instance, is used like discrete choice models. Some of these things are used in horse racing, like which horses to bet on. I mean, so there have been a lot of literature with discrete choice models to deal with this problem. But of course, those methods would not directly apply to what we have here. because we also have differential exposure on different slots. So those techniques have to be modified. And this is something which we are looking into now. But again, I don't have anything brief and concise to say on that right now.
Okay.
We can have a long conversation, but nothing brief right now to say. Thank you.